just a brief outline of what I'll be looking at today. Firstly, a bit of an introduction and some context. The observed climate of Northern Australia, very briefly, and then about the future climate in climate models to make projections. How will average monsoon rainfall change, and how will rainfall variability change? And what is the sensitivity of Northern Australian rainfall to emissions, different emission scenarios? And finally, a bit of a summary about what we do know and what we don't know. So part of the context, I guess, is a recent interest in the idea of developing Northern Australia. There was a white paper released a couple of years ago by the government, and it talked about a focus on increased population and infrastructure for Northern Australia. Northern Australia was to be a frontier of development, and there's a $5 billion North Australian infrastructure facility to provide some concessional loans to encourage that development. So you can see this infographic here showing many cows, some mines, some tourism, some ports, and a great deal of activity in the north, which is obviously something that needs to be taken into account in terms of climate change and what that may bring for Northern Australia before that type of large-scale development can be confidently planned for the future. And another part of the context is the observed increased rainfall trend over northwest Australia over the last 30 to 50 years. So while those of us in the south and the east of Australia have been experiencing...
The wind can hear.
Some people can.
Some people can? Okay, sorry.
While those of us in the south and east have been experiencing drying trends, in the north and the west, there's been an increase in rainfall, and so there has been some suggestions that perhaps some agriculture and population should be shifted to the north. Some of our politicians thought that might be a good idea. But of course, before we should take those kinds of decisions, we need to make sure that we know whether that trend is due to natural variability or external forcing. And the main focus of our work is how it will change in the future. So we're not going to focus so much on the observed trend, but more on the future. I'm sorry for those people that are having trouble with the sound, but I've probably got limited ability to fix it from this end, I think, so I'm just going to continue. So what kind of climate change impacts can Northern Australia expect? Well, the recent Climate Change in Australia report summarised a likely increase in heat waves, likely increase in extreme heavy rainfall, so more floods, fewer but more intense tropical cyclones, and changes to bushfire risk and timing. So these are the kinds of things that are on the horizon. And of course, these kinds of changes will have impacts on many different industries and so forth, for agriculture and ecosystems, human health, disease risk, and for Indigenous communities who tend to be very vulnerable to many of these kinds of impacts. And what is the role of rainfall projections? Well, projections can be very beneficial, obviously, for planning. If we know about the average amount of rainfall changes in the timing of the monsoon onset, this information can be useful for agriculture, water resources, and tourism. Projections of changes in the intensity or frequency of rainfall might be useful for those planning infrastructure, such as roads and bridges, and of course for emergency services. But unfortunately, at the moment, our current rainfall projections are highly uncertain. As you can see down the bottom here, hopefully, we have the future rainfall under a high emissions 8.5 scenario, showing up to more than 25% wetter or 25% drier. So obviously that's a difficult kind of projection for policymakers and decision makers to make use of. We want to understand this uncertainty, and we want to, if possible, reduce this uncertainty by deciding whether some of the models that go into this, this range may be more or less reliable than others. So firstly, starting with our present day climate in Northern Australia, we talk about the monsoon and Northern Australian rainfall more or less interchangeably, because really the vast majority of that, that rainfall is coming from the monsoon. So while we have prevailing southeasterly winds, during the active monsoon period between November to April, we have a moist northwesterly flow that brings in moisture from up here. During early summer, as the continent heats up, low pressure draws the monsoon trough over northern Australia, and this draws in that moist air from the surrounding oceans, initiating deep convection, and that's what we describe as the onset of the Australian summer monsoon. Here is a typical synoptic chart for an active monsoon period, and the monsoon trough is indicated as a dashed line running over the north of Australia, and also actually with a tropical cyclone embedded in that monsoon trough. In terms of the rainfall seasonality, hopefully you can see this box here. This is the sort of domain that we focus on in our study, which has a very strong rainfall seasonality. So in the wet season, it has the majority, almost very, very large fraction of its annual rainfall, and then here in the dry season, very little rain at all. So if you look at Darwin, for example, we have very, very clear seasonality of rainfall with the dry season here, and the onset of the monsoon typically occurring around late December, as defined by wind reversal and widespread heavy rainfall. I should mention the onset date can vary with ENSO conditions. So during an El Nino year, it tends to be a bit later and a bit earlier during the La Nina year. How would the monsoon system be affected by climate change? Well, this is quite a nice graphic from the recent IPCC report, which summarises the present day and the future drivers, if you like, of the monsoon. So a monsoon is driven by contrast between land and ocean, and the onshore flow, and the feedbacks with deep convection. In a warmer world, we'd expect to have an increase in atmospheric moisture, so potentially more rainfall, but there's actually a weakening of that tropical overturning circulation. We expect an enhanced land-ocean temperature gradient because the land will warm more than the ocean surface. And we also consider the role of changes in aerosols, which may have effects on both radiation and clouds. So, as in many other aspects of climate change, it is a complex situation where we have competing factors. Some would favour a stronger monsoon in a warmer climate, and some would favour a weaker monsoon. When we want to look into the future, we may mainly rely on climate projections from global climate models. So in this study, we used around 35 CMIP5 models, the recent generation of global models. Into those models goes scenarios of different kinds of greenhouse gas emissions and other forcing factors. The models are run on a grid across the globe in the atmosphere and the ocean, and provide output of a very wide range of variables, including things such as temperature and rainfall. We look at the globe, but for most purposes, we're interested in a particular region. So here, Northern Australia, how is the temperature over this region? Before we can really use the models to make projections, we need to evaluate them and see whether they actually capture the large-scale features of the monsoon. So here is, on the top, are observed rainfall and winds from CMAP and NSAP, low-level winds, and then below that is the model mean from our 35 coupled models. And hopefully you can see that the model is able to simulate the heavy rainfall over Northern Australia, which is here in the odds and the model in the summer season. So this is December through February. And also a reversal of winds, a westerly flow over just the northern tip of the continent. Another way of looking at the winds is to look at a monsoon shear line where the winds change from easterlies to westerlies. And the observed is the NSAP, the blue dashed line, and hopefully you can see the black line, which is the historical model, runs reasonably similar in the position of that monsoon shear line. There is quite a range, though, of individual models, just shown in the light grey colours there. So looking at a little bit of a different criteria for the models, how well do they simulate the annual cycle? So we've got the annual cycle of precipitation for each of our individual models. So that may be a little hard to see, but hopefully you can see the thick red line, which is the model mean, and the black and black dashed lines are two different observational. So there's a very large spread between the individual models, but the majority of models are able to capture the seasonality of rainfall, and the multi-model means actually observed. In terms of the winds, the models are largely capturing the reversal from easterlies to westerlies, and the multi-model mean again is quite close to the observed. There are a few models that have some problems, but we decided to use all the models in our study and simply explore the full range of uncertainty. So if we look first at the multi-model mean or average change, a whole set of models are under that high emissions 8.5 scenario at the later part of the 21st century, and compare that with the last 30 years of the historical period. You can see the rainfall change that's given here in millimetres per day per degree. It's quite there's quite a weak signal over Northern Australia in the multi-model mean, a slight increase, but there's not much model agreement because these little stipples are the regions where there's a high agreement between the models about whether it's going to get wetter or drier. We'll go into that more in a moment. In terms of the winds, we can see a slight weakening of the monsoon westerly flow. The colours here are the wind strength, so bluer colours are winds that are weakening. Just means that the mean circulation is weakening a little bit as expected. Now, if we look at all the individual models and calculate an average rainfall change over that monsoon box, just shown here over Northern Australia, we find that there's quite a wide range, as I mentioned at the start, around 43% drier up to 37% wetter under the high emissions scenario. So we want to try and understand the difference between those models that are simulating drier and wetter conditions, and we sort of group them into terciles, a dry and a wet tercile. We look at how the rainfall and temperature change for each of those groups. So all the models, and then just the dry models, the ones that get drier, have a coherent pattern, not just over Northern Australia, but also over the equatorial Pacific Ocean. And it's obviously becoming quite a lot wetter in the equatorial Pacific while it's drying over Northern Australia. Whereas the models that become wetter over Australia also have a lot of agreement about the pattern, but they don't seem to have that large increase. So when we subtract those two groups, the largest difference is actually in that western equatorial Pacific region where it becomes wetter in our dry models. If we look at the temperature change for each group of models, the dry models have a more enhanced warming over the equatorial Pacific, whereas the wet models don't have that so much. And the change or the difference between those two clearly shows here the much greater warming in the dry models in the western equatorial Pacific. Another issue, I guess, is to consider the mean state of the models. The models that have that drying over Northern Australia, we look here at the difference between the model climatology and the HADIST observations. They tend to have too cold SSTs in the equatorial Pacific, and particularly in the west here, whereas the wet models don't have such a large bias or error in that equatorial Pacific region. So just to kind of summarise the two main findings of this part of the work, firstly, in terms of the rainfall change, which is shown on the x-axis in both these plots, it's quite strongly correlated with the amount of warming in the western equatorial Pacific. Those models that warm more are becoming drier over Northern Australia. In terms of the bias, a second plot, those models that have a larger bias tend to have a drying, and in particular, there's an outlier, a group of outlying models down here that have very large biases. So we have less confidence in these models, in the ones that have a large bias in the west and equatorial Pacific and simulate relatively large drying, which makes us think that wetter or little change are more likely rainfall projections. The next aspect of the study was to look at rainfall variability. So the IPCC report had some figures summarising changes on a range of different timescales. For the Australian monsoon, they had average change, and then they had change in interannual and also daily timescales. And they found an increased variability, both daily and interannual rainfall for Australia and for other monsoons. But we wanted to know whether this change, this increase in variability, applied on a wider range of timescales. So we want to go to a full range from daily through to decadal. And we want to ask whether this change, this increase in variability, is largely due to a thermodynamic increase in atmospheric moisture, just a simple Clausius-Clapeyron relationship with the warmer atmosphere holding more moisture. Firstly, we looked at just the daily rainfall variability at each grid point and take the standard deviation of that as a simple measure of rainfall variability. On the left-hand side is the Australian summer change in variability from a present day or historical to the RCP 8.5, the high emissions future. And you can hopefully see that there is an increase in variability in Australia, although it's relatively weak compared to some of the changes elsewhere. And in terms of the Northern Hemisphere summer, you can see a very large increase in variability, particularly over South Asia, over India, and also to some extent over East Asia. But beyond that, we wanted to actually look at the different timescales. So we used bandpass filtering of daily rainfall to break up the time series into different bands: a daily, weekly, monthly, intraseasonal, annual, interannual, and decadal bands. And we basically calculate those for the historical climate and then also for our future climate, and we compare the standard deviations of those two time series. When we do that, we end up with a sort of box and whisker plot showing the range for a group of models. So there's around 35 models for the historical climate, the blue boxes, and for the future climate, the pink boxes. And we also plot the AWAP observations on top of the historical, and there's a reasonable agreement for most of the different periods shown along the bottom here, although there's models slightly underestimating annual and decadal variability. But in terms of the difference between historical and our future, these are the grey box and whiskers along the bottom here. They're all showing, the majority of models are showing an increase in variability for each of those different time periods. For those in the kind of sub-annual group, they're actually showing more than 75% of models. So the box is the interquartile range, and more than 75% of models are showing an increase in variability. For the annual and above timescales, it's around, well, it's more than 50% of models. We did compare that to the other two monsoon domains, and when we calculate the percentage change, we've got the same time periods, and now it's the change for the Australian and also the South Asian and the East Asian monsoons. And you can see that there's overall an increase in variability for all three of those monsoon domains. And we did kind of a simplistic calculation of what a Clausius-Clapeyron warming signal might look like to just increase the rainfall by 7% per degree warming for each model. And so we show that by these boxes that sit alongside the actual model change just for the Australian monsoon domain on the right. And we find that actually the model's change is slightly less than that kind of idealized thermodynamic response that we calculated. So there may be some other factors that are actually counteracting the simple increase in moisture and therefore heavier rainfall in the warmer world. So just to summarise that part of the study, we looked at rainfall variability on timescales from daily to decadal and found that there was an increase in that variability. What would that mean in the real world? That would mean potentially an increase in intraseasonal variability, so more intense active monsoon periods, and maybe also longer break periods. Larger rainfall response to ENSO and to Pacific decadal variability, which is consistent with other work, and more floods and potentially also more droughts, so a less reliable water resource So obviously those are kind of issues for people planning development for Northern Australia to take into consideration. The final part of the study looked at different emission scenarios. And of course, a lot of our work is focused on the high emissions 8.5 scenario, but there is interest in looking at lower stabilisation and decline scenarios. So 8.5 basically keeps going to business as usual until the end of the 21st century, whereas 4.5, RCP 4.5 is a scenario where we actually have stabilisation by the end of the century, whereas RCP 2.6 is more like a Paris Agreement type of stabilisation and hopefully under 2 degrees scenario. So we look at those three. We don't actually look at RCP 6 in this study. In terms of the aerosol forcing in the different RCPs, anthropogenic aerosols, which is what I'm talking about here, I'm not talking at all about volcanic aerosols in this discussion, have been observed to increase over the historical period with industrial activity and peak around 1980, but then have a prescribed or predicted decline in the future with increased pollution controls. And so for each of the scenarios, you can see the path that those aerosol emissions are expected to take in the future. What does Northern Australian rainfall look like, broadly speaking, in the different RCPs? In our high emission scenario, as we looked at before, we have a very wide model spread, but the multi-model mean, the black thick line, shows little change. These are the figures from the Climate Change in Australia report from a couple of years back. Similarly, under the medium and low emissions cases, there's also the multi-model mean change is also near zero. The model spread seems to favour drier conditions for the two lower emissions scenarios, more so than increased rainfall. So we want to understand, are these rainfall responses simply scaling with warming, or is there also a response to the aerosol forcing, the future change or reduction in aerosol concentrations? Why am I talking about aerosols and rainfall? Well, there are a couple of different effects that we're mostly concerned with. There's the direct and the indirect effect. This is obviously a very simple kind of summary of aerosol chemistry, and I refer you to Matt Woodhouse's webinar of several months ago for a much more complicated treatment. But in terms of the direct effect, basically aerosols would scatter and absorb incoming radiation, leading to cooling at the surface. The indirect effect is aerosol cloud interactions. So aerosols acting as cloud condensation nuclei, changing cloud albedo and lifetime. And it's actually been found in recent work that that second set of effects, the indirect effects, are the ones that produce the main response in precipitation to aerosol forcing. So these are the ones that we will be focusing on. There has been some work linking observed trends in monsoon rainfall to aerosol changes. So, for example, Leon Rothstein and colleagues at CSIRO suggested that there may be a role for aerosols in forcing the observed increase in northwest Australian rainfall. I don't want to go into that here because it is still very much an active area of research, and I don't think that the final consensus has really been formed on what is actually driving this observed trend. It may be a combination of forcing, external forcing and natural variability. There is an observed weakening of the South Asian or Indian summer monsoon, and that has been probably more clearly linked to the recent increase in aerosols over that period. What does the aerosol climate signal look like? Well, we can look at some models run with just aerosols for the historical period, anthropogenic aerosol only runs, to look at that spatial pattern. And we can see the change in temperature if we subtract a mean cooling signal. I'm just going to close the blind, sorry, it's very bright. Sorry about that. there's actually a mean cooling signal that we subtract, and then we end up with a larger cool anomaly in the northern hemisphere and relatively less cooling or relative warming in the south. And that drives a rainfall response with a drying in the northern hemisphere and a weak increase to the south. So that's a kind of an idealized experiment where we have aerosols increasing in the historical period. Of course, in the real world, we didn't just have aerosols increasing, we also had greenhouse gases increasing. So if we look at the greenhouse gas pattern, this is from runs just with greenhouse gases now on the left-hand side. This actually favours a greater heating in the northern hemisphere, so more land, and land heats up more than ocean, and we end up with this asymmetry between north and south. And as you may be able to see, it's very similar but opposite to that in the aerosol pattern. So in terms of the historical period, these two patterns, or the gradients, if you like, more or less cancel out, and we end up with little asymmetry between north and south in the 20th century, in the historical period. But if we look at the future, of course, as we take the aerosols away with pollution controls, this pattern will now reverse, and we will now have this greenhouse gas pattern and favouring northern hemisphere warming, and similarly an aerosol reduction pattern also favouring northern hemisphere warming, and potentially drawing or displacing rainfall northwards into the northern hemisphere. Excuse me. Unfortunately, the models that we use, the CMIP5 models, only some of those models actually capture or include both the direct and the indirect aerosol effect. There was a study by Leon Rothstein and colleagues that divided these models into two groups. The high force were the ones that have both indirect and direct effects, and the low force were those only having the direct effect. And they found that the high force models have a much larger aerosol response, consistent with what I've been saying. So there's an asymmetry in temperature and rainfall in the runs, both historical and future runs using these high force models. So we take advantage of this distinction. We don't have future runs with and without aerosol forcing, which would be obviously the ideal experiment to look at. Instead, we're going to use the low force and high force groups as kind of a proxy for what would the future runs be with and without aerosol forcing. Obviously, it's not that simple, because the low force models do have some sensitivity, but it's much weaker than the high force group. So we asked the question, are the Australian monsoon projections different for the high force and low force group of models? Firstly, I looked at the asymmetry, just taking the average rainfall in the north between 0 and 20 north, minus the average rainfall in the southern hemisphere between 0 and 20 south. So this is the zonal average right around the globe for those two bands. And it's just a measure of the basically the asymmetry in rainfall between northern and southern hemispheres. We've got the historical runs, and then up the top the low force models, and down the bottom the high force models, and we're looking at 2.6, so our relatively low emissions scenario here. Hopefully you can see that there's little change in the low force case, but the high force models are showing a positive trend, so the rainfall is basically shifting to the north in those models. In the future, in 4.5, there's a weak increase in asymmetry, a northward shift in the low force models, but quite a strong northward shift in the high force models. And once we get to 8.5, our high emissions case, you can see now that the high force models have a very strong asymmetry, a very strong displacement northwards of tropical rainfall. In terms of the spatial pattern of rainfall change, our low force at the top here, under 2.6 conditions, this is the difference between 2.6 and historical, have little change over northern Australia, whereas the high force models, the ones with aerosol sensitivity and indirect effect, show a strong drying over northern Australia and a strong increase in rainfall over both the South Asian and the East Asian monsoon domains. So this could be at least partly driven by that aerosol signal. If we look at 4.5, we're now starting to see somewhat wetter conditions over both the Asian monsoon and the Northern Australia or Maritime Continent region in the low force models, but in the high force, dry to the south and wet to the north in the Northern Hemisphere monsoon region. And finally, the change in the in the high emissions case is stronger again. And in particular, you can see this very clear asymmetry for the high force models, where it's becoming drier to the south and wetter to the north. So the final question is what's happening over Northern Australia itself. We take the area average rainfall change over Northern Australian box. The low force models have little trend in the future under 2.6, whereas the high force models are showing a drying trend in the multi-model mean, and a large proportion of models are showing a drying trend. Under 4.5 now, start to see an increase in those low force models, the ones that don't have a lot of aerosol sensitivity, and the high force models are still showing a drying signal. And finally, when we look at our high emissions case, now we can pretty clearly see the low force models are responding to warming as the greenhouse gas forcing is greater with an increase in rainfall here. Whereas the high force models are still showing a multi-model mean drying, although with quite a large model spread. So the models without indirect effects, the low force models, really just have an increase in rainfall following the amount of warming in each of the scenarios, while the high force models seem to be drying in response to the aerosols, but also have a kind of counterbalancing increase due to greenhouse gases, and that's at least part of the explanation for this large model spread that we see for that group of models. So just to summarise, I guess, all these different threads, what do we know? Well, the direction of change of Northern Australian rainfall is unfortunately still quite uncertain, but we know a bit more about why. The model spread is due to differences in the SST warming pattern. It's due to different biases in the mean climatology of the models. It's due to the amount of warming, which varies from model to model, and also to how well or how sensitively the models respond to aerosol effects. Model mean rainfall change is correlated with the amount of warming in the Western Equatorial Pacific. This region's very important for our Northern Australian rainfall. So the models that project large future drying in the north of Australia, we find are less reliable because they have those big biases in SSTs in the Western Equatorial Pacific. Models with indirect aerosol effects simulate large future Northern Hemisphere warming and a northward shift of tropical rainfall. So over Northern Australia, this may lead to drying, but we did find a compensating increase due to mean warming, and that produces a large model range. Unfortunately, models that project very large increases in rainfall may be less reliable than the ones that don't fully capture this aerosol sensitivity. There's a couple of references down the bottom there that you can look up for more details about those studies. And finally, what don't we know? Well, we definitely know that there's a sensitivity of the rainfall change to the pattern of SST warming. This remains a large source of uncertainty. So we're planning to carry out a series of access model experiments to try to better understand the contribution of model biases versus model differences in SST warming pattern. It's not clear whether the changes in rainfall variability are due to changes in frequency or intensity of rainfall. We want to further investigate changes in the interseasonal variability of monsoon rainfall. And finally, the role of aerosols versus greenhouse gas forcing. Really, we need some targeted experiments to really get to the bottom of that. And we're going to take advantage of the next generation of climate model simulations, the CNIP6 models, to further address this question. Thank you very much.
Great. Well, thank you, Jo, and thanks for managing so well with the IT issues. Can you hear me okay, Jo?
You're very quiet, but I can hear you.
Okay, I'll try to speak up. So
That's better.
Thank you again to everyone for tuning in, and apologies again for the technical issues we had. Thank you very much for your patience. If there's any questions, just stick them down the bottom in the chat. We don't have a lot of time due to the issues we've had. But what I will do is I will get a recording of this presentation or Joe to do another recording if it doesn't work out well. And I'll ensure that all participants are sent that recording. And if you have any questions, I'll CC in Joe and you can ask the questions directly to Joe. So thank you once again for attending. Apologies. Next time it will be a lot smoother, I'm sure. And just on that note, the next Earth Systems and Climate Change Hub webinar will be held on the 19th of June at 2:30 to 3:30 p.m. And it will be a presentation by Professor Stephen Fuera on nature-based opportunities for climate mitigation and adaptation in the coastal zone. So stay tuned for that. I'm sure an invitation will be sent out in the next few weeks. So thank you once again, and thank you, Joe. Thank you.